SwayamPrabha. Digital India. Educated India.
Hello and welcome to the discussion sessions of the Production Technology Theory and Practice series of lectures. Now, let me remind you that we have started discussing in our last session the NC and the CNC machines, computer numerically controlled machines. Okay. Now, there what we said is that because of the greater flexibility, basically the numerically controlled machines came into picture, and the greatest advantage of the NC CNC machines is that it can have more flexibility in comparison to the conventional machining, because we have the prime mover in various axes, the individually, and therefore, all the axes can be moved as per our choice, and various relative movement between the tool and the workpiece can be given. Okay, now, what we discussed last time is the program input device, and the program input device we said is the means for part program to be entered into the CNC control. Okay. Now, machine control unit, this is another unit which we said as the brain of the machine, okay, or this is the heart of the CNC system. This is used to perform the following functions: to read the coded instructions, all right, to decode the coded instructions, to implement interpolations. Implement interpolation means whether the tool has to move linearly or the tool has to make a circular movement. Okay, this has to be made, that decision has to be made by this according to the program. It can also have a helical movement, okay, to generate axis motion commands, okay, to feed the axis motion commands to the amplifier circuits for driving the axis mechanisms, to receive the feedback signals of position and speed for each drive axis. So, here what happens is, it is not only that the simply program is given or the signal is given, but there is a feedback that is taken. Okay. We will discuss that what are these kind of feedbacks, what kind of feedbacks are used here. Now, the feedback means that once the signal is going, for example, the signal has gone that the tool has to move linearly by 5 millimeter, let us say. So, whether the tool has really moved 5 millimeters or it has moved only by 4.98 millimeter or 5.01 millimeter, that has to be monitored, and this feedback will be sent to the machine control unit, so that it can actually have a tracking, proper tracking of the movement. And if the tool has not moved according to the desired program, then the machine control unit will make the correction. Okay. It will give some additional signal to the mover, to the prime mover, so that the tool movement can be corrected. This is the receiving of the feedback signals of positioning, okay, and speed. Next is to implement auxiliary control functions such as coolant or spindle on off, okay, and the tool change. So, all these functions are coded in the program, and the machine control unit has to understand what is the code by the program given and accordingly execute the program. Now, another one of course is the hardware, that is the machine tool. CNC controls are used to control various types of machine tools. Regardless of which type of machine tool is controlled, it always has a slide table and a spindle to control the position and the speed. The machine table is controlled in the x and y axis, while the spindle runs along the z axis. This is the normal standard for the normal standard procedure. Okay. Feedback system, the feedback system is also referred to as the measuring system. Okay. Sometimes the feedback system is called, that is the measuring system. It uses position and speed transducers to continuously monitor the position at which the cutting tool is located at any particular instant. So, just now I talked to you about the feedback system, that we have to see whether the tool has been positioned according to the program which is given, according to our requirement. All right. Now, if it is not, then the correction has to be made. So, for that we need to have the different kind of transducers positioned. Okay. Now, the transducer, one transducer could be that it will sense the signal of the tool movement as per length, okay, and it will calculate that how much the tool has moved. Okay. Then that signal will be given to the machine control unit, and the machine control unit will take the decision subsequently. All right. The MCU, which is the machine control unit, uses the difference between the reference signals and feedback signals to generate the control signals for correcting position and the speed errors. So, I will show you later in a block diagram that how this function is actually carried out. Okay. Drive system. Drives are used to provide the controlled motion to the CNC elements. Okay. This to move the like our prime mover, as I said about the prime mover. So, this is moving the spindle, okay, or moving the lead screw for the feed movement and so on. Now, a drive system consists of amplifier circuits, drive motors and ball lead screws, as I said. The machine control unit feeds the control signals, that is positioning control and the speed control of each axis to the amplifier circuit separately. It will be along the x axis or along the z axis. These movements, in case of turning, these movements will be recorded and this movement will be sensed by the transducer, and it will be sent to the machine control unit. Okay. The control signals are augmented to actuate drive motors, which in turn rotate the ball lead screws to position the machine table. This is how it is executed. It will come to the machine control unit will compare it with the reference signal, and it will generate the error signal. Error signal is nothing but the signal that is required to correct the position if it is not proper, or correct the speed if it is not proper, and so on. These are the drives of the NC machines. They could be these drives could be either the hydraulic drives or the DC motors or the stepper motors. Now, hydraulic drives, these are used in relatively high powered NC systems where the higher power is required. All right. Now, the hydraulic system, as you understand, that they have the higher torque carrying capacity. Okay. And the very big advantage of the hydraulic drives is that the hydraulic drives are compact, and with the small design, that compactness in comparison to an electric motor, their power is much more. Okay. For smaller size valves, for example, hydraulic valves, they have a lot of power, or the hydraulic drives or the actuators, their sizes are not very big, not as much as the electrical motors, but their power is they are more powerful. Okay. So, overall their torque carrying capacity is higher. Okay. Now, if you see here the hydraulic drives, this is the details of the hydraulic drive, that it is the actuating signal is given to the servo valve amplifier. So, here through the servo valve amplifier, the actuating signal is amplified and it is given to the servo valve. Servo valve is nothing but opening or closing a port, okay, through which the signal goes. All right. And that actually that is sent to the hydraulic motor. So, hydraulic motor, to the hydraulic motor, the hydraulic power supply is connected, okay, and hydraulic power supply gets the hydraulic fluid from the sump from here, all right. Now, the hydraulic motor in its turn, depending on the signal it is coming from the actuating signal, it gets the required amount of fluid to the hydraulic motor and therefore, the pressure. So, it will actually create the torque and it will rotate the lead screw. On the lead screw, we will have the table with the tool post or whatever is required there depending on the machine, and the table with the tool will be moving along the lead screw to the left or to the right depending on the signal that has been given through the hydraulic motor, and it is in its turn the hydraulic motor will get the signal from the actuating signal and the servo valve. Okay. So, after hydraulic motor completes the operation, okay, at the exit we have the used oil. So, that used oil is filtered, this is cleaned and comes to the sump. From the sump, with the help of the pump, it is pumped to the hydraulic power supply once again, and the whole thing is repeated, all right. Now, hydraulic power supply, this has a complete diagram is shown here. Hydraulic power supply has a 3-phase electric motor, okay, and the pump. So, the pump through the filters, the used oil comes through the filter to the pump, okay. So, used oil come from here, from the sump. So, here we have the filter, and through the filter it goes to the pump, from the pump it goes to the motor, okay. So, from the pump it has the filters also, and through the filters the fluid which will actually come from this used oil, okay. So, this fluid will or oil, this will be going through the check and the pressure valves, okay, and then it will go to different axes of the motor X, Y or Z, all right. In between the valves and the outlet, we have the accumulator, all right. Now, check valve, for example, here for restricting the flow from accumulator back into the pump. So, it may so happen that the accumulator has pressure is high and the fluid can actually go back to the pump and the motor because of this. So, this check valve will stop that movement, stop that flow, okay, and it restricts the flow from the accumulator back to the pump, it will not allow, okay. Pressure valve, whereas for controlling the supply pressure to the servo system. So, this will actually control that whatever supply pressure is required, this much will be provided. If it is less, for example, in that case the accumulator will be activated, it stores hydraulic energy and for smoothing the pulsating flow. So, if it is if suppose it fails, okay, or pressure becomes low, then it will activate the accumulator, and from the accumulator it will actually go to the axis, all right, and so on. So, this in fact checks the or controls the supply pressure to the servo system. This is the servo system, different axis. So, the entire system is it is in here, okay, and from here it goes to the I mean this arrow is to the axis of the motor. So, this is the hydraulic motor. So, in this motor there could be 3 motors on the 3 axis, or if it is a 5 axis machine and so on. Here one axis is shown which goes to the hydraulic motor, and the hydraulic motor rotates the lead screw along with the table. Okay. So, this is the system of the hydraulic motor. Now, in the case of hydraulic motor, as I said, that is the greatest advantage, that it has a very high torque carrying capacity and their sizes are very small, they are very compact. Okay. Now, of course, hydraulic drives have the disadvantage also. One very big disadvantage is that the oil has to be absolutely cleaned. Okay. If any dirt comes, see what happens is these servo valves, they are very complicated and their ports are very small. So, in case a dirt comes in and accumulates in the port, the servo valve will not work. all right, and that movement may be in micron. The movement of the valve can be in micron to open or close the port. Okay. So, if a dirt comes in and gets accumulated in those ports, the entire valve can get clogged. That is one thing. Second thing is that when the whole system works, the temperature evolves, okay, temperature rises, and at that temperature the viscosity of the fluid, that is oil, it can be actually changed. That is another disadvantage. So, therefore, viscosity may not be constant depending on the temperature, if the temperature varies. And the next disadvantage is that the hydraulic system will always have some sort of leakage. Okay. So, see, for example, when it goes through the servo valve, all right, or it goes through the actuator, okay, hydraulic cylinders, there always will have some sort of leakage. Okay. So, small amount, but it can be a small leakage, and that has to be taken into consideration. So, in many designs, the design has to take care so that the leakage is eliminated or the leakage is minimum, and there are many designs in the hydraulic cylinders, so that the the leakage is minimum. Okay. These are the DC drives. So, direct current mostly used drive for the NC machines. DC motors are very popular, since its voltage and speed can be varied smoothly and easily regulated. So, for control it is very convenient, okay, because you see here its voltage and speed that can be smoothly varied, okay, and can be regulated very easily. Principle of operation is based on the rotation of an armature winding, and this is the armature winding here it is shown, and this one, okay, within a magnetic field. So, this armature will be rotated depending on the winding, okay, and depending on the magnetic field that we have. So, this is the armature, okay, and here also we have the winding. So, this is of course not a clear, not a detailed picture, but you must have seen the detailed picture of the motors. So, this is the armature and the armature winding, and which is rotating within the magnetic field. This can be used as a generator or as a motor, all right. So, it can actually, the shaft can be rotated and it will produce electricity, or if you pass the electricity, the shaft will be rotated. When the shaft is rotated, this is actually works as a motor, or if the shaft is rotated by an external source of energy, and then this power can be created. So, this is then this works as a generator. Okay. Here you can see that A is given as a this the rotor, okay. B is the starter winding, this one, and the C is the commutator. Okay. Commutator is to take the current, because shaft is rotating. So, there is a commutator which is required here. Okay. The third type of motors, that is prime mover, these are the stepper motors. Now, the stepper motors, they are actually of course not very high torque carrying capacity like DC motors or hydraulic drives. So, therefore, the stepper motors are used when the machines are of smaller size, basically they are not very high torque carrying capacity. Okay. So, stepper motors, the diagram, schematic diagram shown here, this is an incremental digital control device, okay, and the stepper motors translate an input pulse sequence into a proportional angular movement. Okay. So, input is given to the coil, to the driver, to the drive from the outer external source, which is some kind of a pulse, okay, and that pulse will be given in a sequence, and then as a result the output will be the rotation of the rotor, okay, angular increment. So, one angular increment step for each input pulse, that is the kind of the rotation it may have, or it may have other the scale. For example, For each input it may also have the half rotating, or in each input pulse there can be 2 rotating. So, that depends on what kind of stepper motor it is and what kind of winding we have in the rotor, in the starter, and so on. Okay. The shaft position is determined by the number of pulses, the number of pulses given here at the input. So, the shaft position is determined by the number of pulses, and its velocity, that what is the speed of this shaft, that depends on the frequency, pulse frequency, at which frequency the pulses are given. Okay. So, one thing is the number of pulses, how many pulses we are giving, or another thing is that by which frequency the pulses are given. So, number determines the position, that how much it will be moving and then it will take a position, and then how fast it will be moving, the velocity, that is determined by the pulse frequency. Okay. The shaft speed in steps per second is equal to the incoming frequency in the pulse per second. This is what it is said, that the velocity is determined by the pulse frequency. Okay. This is the pulse frequency and this is the velocity, that is the speed, shaft speed. An electronic switch is used as a driving unit. So, this electronic switch, actually this can be automated to make the changeover from one coil to another coil, so that the rotor can be rotated either in this way or in this way, that is clockwise or the anti-clockwise direction. Okay. So, this is the switch, that switching system will take the or determine the rotation of the rotor, in one word. Okay. So, here is the starter, there is a winding, and the rotor will rotate depending on the input pulses which are given. Okay. And this is explained here, that this rotor is the shaft. Okay. This is the shaft which you are actually rotating or you are positioning. So, positioning will depend by the number of pulses you are providing to the input system, to the input circuit, and what is the frequency of the pulse that is provided, that determines the speed of the shaft or speed of the rotor. Okay. All right. Now, let us talk about the interpolation. Let us see what is that interpolation. Okay. Now, interpolation is to calculate the intermediate points of a curve given its starting and the end coordinates. So, I told you earlier also that when the tool has to move, let us say from one point to another point in a linear movement. Okay. So, there we have to calculate the coordinates from which point to which point it is moving, and then accordingly we give the movement or the program or the signal to the tool, that is called the interpolation. Okay. Or the tool can go from one point to another point in a circular way. Okay. So, depending on the radius or the diameter of the curve and the coordinates, we will accordingly give the signal to the tool, and the tool will be moving exactly according to that path. That will be the circular interpolation. Okay. So, to calculate the intermediate points of a curve given its starting and the end coordinates, two coordinates are given, starting and end, and intermediate coordinates it has to be calculated. So, depending on the intermediate coordinates, you understand that the tool can move linearly or circular, in a circular way. Required for machining straight surfaces that are not parallel to either of the coordinate axis. Okay. If it is parallel to the x axis here in the turning, or y axis here in the turning, so in that case there is no problem, because you are asking the tool to move according to the x. You write in the program that x and y it will move, all right. But if we want to move it not parallel to any of these axes, in that case we have to say that what should be the interpolation, either it will be the linear interpolation or it will be the circular interpolation. Okay. Now, the types of interpolation, as I was telling, it can be linear, it can be circular, it can be parabolic. Okay. So, linear, circular and parabolic, these are the three types of interpolation which are popularly used in the programming or in the CNC machines. Depending upon whether the given profile is approximated with the help of straight lines, arcs of circle, or segments of a parabola. Segment of a parabola is the parabolic interpolation. Okay. Segment of arcs of circles So, this is the circular interpolation and so on. So, let us see how it can be done. Linear interpolation. So, we have the x and y coordinate. Let us say it is, we are writing it this way, x and y coordinate. Okay. Now, coordinates of successive intermediate points, that is, if x 1 y 1 is the starting point and x 2 y 2 is the end point. In that case, these successive intermediate points can be calculated from the consideration that distances x 2 minus x 1 and the y 2 minus y 1 must be travelled in equal time, okay, because it is a straight line. All right. So, therefore, the intermediate points will be x s, successive intermediate points. This is x 1 plus, let us say, sum of s 1 to n, okay, number x 2 minus x 1 divided by n number, all right, and the y s is similarly y 1 plus y 2 minus y 1 divided by n. This is from 1 to n, all points summing up from 1 to n. N is the total number of steps between the A to B. So, depending on the step that you are taking, 1 here, suppose 2 here and so on, n value will be accordingly varied, okay, and you can find out that what is the coordinate for next to next to next and so on, and then the join these coordinates. This joining will be done by the machine. This coordinate will be calculated, intermediate coordinates will be calculated by the machine control unit, MCU. That is why we said that this is the brain or heart of the machine. Okay. We are only giving in the program that what is the, we are only saying in the program, we will see it later, that we need the interpolation or the linear interpolation, and we are giving the coordinate of x and coordinate of x 1 and y 1 and the coordinate of x 2 y 2. These are the coordinates which are actually the 2 points in beginning and the ending, and the tool will decide that how to go. Okay. Now, why to calculate the intermediate points? Because it will be the shortest path that the interpolation will calculate, okay, according to, of course, our drawing, and the S is the sequence number of the particular step, that is s equal to 1, 2, 3 and so on, that you understand. Now, xs here in this case, if it is given as the a x 1 y 1 and x 2 y 2 coordinate is given x 2 y 2 here as a b, okay, and this is the center of this circle, this is the path or the sector of a circle. So, in that case, the x s is x of mu, let us say some point, and this will be x 1 minus y into s minus 1 minus y m divided by n from 1 to mu, let us say there are mu numbers. Okay. So, here the n is also the total number of steps between a and b, okay, like in here. S is the sequence number, same thing. Mu is the instantaneous value of the stepwise change in the S. What is the value, next value and so on. So, in that case, with the O as center, the tool will be moving from A to B, okay, with this interpolation. So, we have to, in the program, again we are telling in the program that we need the circular interpolation. There is a code for circular interpolation or there is a code for the linear interpolation. Now, where it is used, let me also tell you, like circular the linear interpolation, for example, this is the turning lathe, okay, turning CNC turning machine. Okay. In that case, the tool point has to move from one point to another point, or the drill has to move from one point to another point. Okay. So, there it is, if it is not parallel to x or y axis, then we have to say that it is a linear interpolation, because we are linearly moving. Okay. In case we have to make a contour, then we have to tell that there is a movement that is required in the semicircular movement. And for example, in case of milling cutter, okay, in case of milling cutter, we need to give a profile, we need to cut a profile, and for that profile we need to have the movement of the milling cutter, end milling cutter, for example, in a circular interpolation. Okay. So, we have to give the coordinates and so on. So, this is the formula that will be used by the machine control unit to calculate the coordinates of the intermediate points. Okay. This is the theory behind this, and it will finally move the tool from one point to the another point which we have designated, which we have actually set there. Now, if we see the types of the computer numerically controlled, that means what types of numerically controlled controls exist. Now, there are different types based on the motion type. We have the point to point control, straight cut control, or the continuous path control. Okay. Based on the control loops, we have the open loop or the closed loop systems. I will explain each of them in details. Now, based on the power supply, we have either electric or the hydraulic, okay, or the pneumatic. Based on the positioning system, we have the incremental or the absolute. So, these things we will discuss now one by one. Now, based on the motion type, we said that there is point to point, straight cut, and the continuous path. Okay. These are the examples. Now, point to point, that is no contouring capability. Here is the example. That means, suppose we have a drill, okay, or we have let us say spot welding machine or the spot welding head. So, the spot welding has to be moved from one place to another place. Okay. So, let us say the manipulator or the robot hand is holding that and it is moving from one place to another place, or the drilling machine is moving the drill spindle with the drill. After it drilled a hole, it has to come up, come out, and then it will move to another position. Okay. So, this is point to point, and here what happens, the in this the how the tool will be moving, that is not important, but only the coordinates will be given from the from one point to another point. Okay. Now, here in the point to point, no contouring capability, in the sense that it can actually move only in the linear way, all right. It cannot move in the circular way, not as per the contour, all right. Now, the straight cut control, one axis motion at a time is controlled for machining. Now, the straight cut control is shown here. That means, in this example what is said is that the end milling cutter, this is moving along one parallel to one of the axis, either parallel to this axis or parallel to this axis. It is actually also can be said, you know, in the case of the turning. Let us say we have to turn this workpiece, all right, and now the tool is here, and this tool can move either in this direction, okay, when it is facing is required, or in this direction when the turning process is required. So, it will move like this, then it can move from here to here, then it can move from here to here, and so on. So, that means it is moving either parallel to this axis or parallel to this axis. So, in this turning case, we said that this is x and this is the z, all right. So, either it is along the z or along the y, along the x. So, x also can be moved to face this and so on. So, this is shown here that the tool, either it is a turning tool or it is a milling cutter, okay. The tool can move at a time parallel to one of the axis, either x axis or z axis, is in case of turning, but in case of milling it is x and y. Okay. So, the third one is the contouring. Contouring is the multiple axis controlled simultaneously. That means, in that case, let us say we have a milling end milling cutter, and the end milling cutter is required to make a contour groove, okay, here. So, this contour groove, to make that, the tool has to move in a very complicated path like this. So, that means we have to then control both the axes together. So, this is contouring, which is not possible with the help of the straight cut control, okay, or with the help of the point to point control. But if you see that capability of the contouring control, then you will realize that the contouring control, okay, this can be used for of course, straight cut control or the point to point control, isn't it, that you understand. Or for example, this one straight cut control, this cannot be used for contouring control, but this can be used for point to point control, because this capability it has. But point to point control is the easiest, and this is the simplest, this is the cheapest. This is used only for the point to point and cannot be used for straight path control or straight cut control or the contouring, all right. But greater versions like contouring can be used for both of them, this can be used for the point to point and so on. Okay. Types of CNC based on the control loop, as I told you, mentioned it somewhere, that there could be the feedback control systems, okay, or it can be an open loop control system. Let us say in that case the pulse trend, that is the input signal, is given to the stepping motor, okay, and the stepping motor, which we already discussed, that for each pulse the motor can be rotated at a certain angular angle, okay. So, let us say this is the movement of the stepper motor output shaft depending on the input pulses given, okay, and with the gear train this will be then moving the lead screw, and on the lead screw we have the work table along with the workpiece. So, the workpiece will be moving either to the right side or to the left side on the lead screw, all right. Now, the pulse train, let us say we are giving the signal here in the input for stepping motor to move to a certain degree, okay, rotation, but whether that has been accomplished or not, that we are not measuring at the output. So, output is open, okay. That is why it is called the open loop control system. Of course, those open loop control systems are cheaper, it is easier, and we can use them when we are absolutely sure that whatever the input command we are giving or input signal we are giving to the mover, okay, the output signal will be accordingly. So, it will be precise movement or it will be precise motor. So, then we do not need to check the output, need to control the output, okay. But when we have to control very precisely that whether the input signal is actually being followed at the output, then we need to have the feedback control, okay. And the feedback control is like that here is the input signal, this is a comparator, okay. This is the DAC, that is the this is converter, this is the DC servo motor, okay. This is the converting digital to analog, because this is the servo motor, okay. And this servo motor will rotate the gear train, and in its turn it will rotate the lead screw with the work table, all right. After that, how much it is moving, that is being sensed by a position sensor, which is absent here, as you can see this. So, that position sensor, depending on the signal which is given to the input, okay, the lead screw will be moving along with the work table, this will be sensed, and this sensor signal will be sent to the input, okay. The input and this signal will be compared in this comparator, okay, and the error signal is produced. Error signal is something which is the discrepancy between the input and the output signal, if any. So, suppose according to the input signal, the work table has to move, let us say 20 millimeter, and it has moved to 19.5 millimeter, let us say. So, there is a discrepancy of 0.5 millimeter, okay. So, this discrepancy signal, that is in terms of the error signal, that is in control technology it is called the error signal. This error signal is the discrepancy between the input and the output signal. It is generated so that in the performance of the device is improved, so that it can be corrected, okay. So, the error signal is again converted digital to analog, and this is given along with the input to the DC servo motor to tell that the output is not as per the desired level, and it has to be improved, it has to be corrected. So, the DC motor accordingly give the correction, moves more or moves less, so that the positioning can be done accordingly according to the input signal. So, you can see that this is a closed loop control system. That means, the feedback is continuously monitored, and accordingly the compensation is given to the input, so that the output signal can be corrected if it is not according to the input signal. Okay. So, both these systems can be utilized. We will discuss a little more about the feedback system in terms of the adaptive feedback system, adaptive feedback control, how they work, because most of the modern machines, particularly the NC and the CNC machines, they are fitted with the adaptive control systems, and they are very useful because they improve the performance of the machine. All right. Once more, these are more complicated because you know that we have to have a position sensor, and it is the not only the directly it can be given to the input, but it has to be then it has to go through the pre-amplifier and the amplifier to amplify the signal, because the sensor signal from the sensor can be very weak. So, it has to be amplified. So, there has to be a pre-amplifier to pre-amplify that, and then amplify the signal, okay, coming from the pre-amplifier. Then this signal can be put in the input or given in the input. Okay. So, sometimes the phase also can be changed. So, if the phase has to be changed, then there has to be a phase changer, and then the output from the phase changer has to be supplied to the input. Then the input and this signal will be compared, and so on. So, therefore, these systems are more expensive, complicated, okay, but they are more accurate, because the output signal is always measured, monitored and corrected. Okay. The output signal we can say that it is always as per the input signal, as per the desired level. That is why these are more accurate and more reliable. Okay. Open loop, these are the things which are written here. I have already told that open loop limitations are that control unit assumes the desired position in the chip. Okay. So, there is no compensation, and typically a lower torque motor like stepping motors are the lower torque motors, lower torque carrying capacity. Whereas, in case of open loop, the advantages are the less complex, less costly and lower maintenance costs. Okay. These are the open loop advantages. Whereas, the closed loop advantages are that the DC motors have the ability to reverse instantly to adjust for positioning error. So, whether it will be plus or minus, this can be instantaneously done by the DC motors. All right. The error compensation allows for greater positional accuracy, and positional accuracy can be of this value 0.0001 inch. Now, the DC motors have higher torque ranges against the stepper motors, all right, and the only limitation is that it is complicated. So, therefore, it is more expensive, because we have to have a transducer and we have to have a loop. This is the feedback signal with an amplifier, pre-amplifier and so on. Now, as I said that let us discuss a little bit about the adaptive control system. What are the adaptive control systems? Adaptive control systems, they are the closed loop feedback control systems, which are fitted in the many of the NC and the CNC machines, particularly the modern NC and the CNC machines, so that the output can be always monitored and output can be always compensated for. Okay. Now, let me give you an example that why these adaptive control systems are required. Let us say we have the turning, this is simple process, okay, and we have calculated the force required for the turning depending on the parameters, depending on the tool and the workpiece material combination, okay, and we have selected a tool for a certain hardness of the workpiece material. All right. Now, the hardness, by hardness we assume that the hardness is homogeneous, all right, but while cutting that cylindrical piece in the turning lathe, in between at certain depth we have encountered a carbide particle which is very hard particle, all right. Now, the tool, when it is encountering the carbide particle which is embedded there, the force goes very high because it is actually the very hard particle. For that high force, the process was not calculated and the tool can actually break, all right. Whereas, if the feedback control or the adaptive control is used, in that case that will be automatically sensed and immediately the tool will be retracted back, so that this can be avoided, this breakage of the tool can be avoided. Or in some cases there are some adaptive control systems where if the force exceeds, in that case the entire process will be stopped. Okay. So, you will be knowing that something happened, that the force has exceeded, all right, and it can be eliminated and so on. In some adaptive control systems, it adapts itself, so that the process continues and the system does not break down, all right, and so on. So, let us discuss this. Although NC has a significant effect on downtime, it can do relatively little to reduce the in process time. Let me give you little more details, because we have not talked about the downtime or the in process time. NC, that is numerically controlled, it can actually reduce the downtime. It can reduce the downtime, means when the machine is not working, machine has failed, it has stopped, it is not working, all right. But it cannot do much about the in process time. See, the machining time is something which we have said, that we have the L, that is the length, and that divided by n into f feed, okay, that is the time taken for machining a particular length. Okay. Now, the NC machine cannot change that f, that feed, all right. That is why L is constant, that is the length of the workpiece, divided by n is constant, this is the RPM, but f it can be varied. But f is not varied in the conventional system, where there is no NC system, all right. F is constant, and therefore, the time taken is constant in the NC machine as well. Okay. So, therefore, the NC system, using these constant parameters, it has no leverage, no possibilities to change the machining time, and changing the machining time means that it will actually accelerate the production rate. Okay. But in case of adaptive control system, these systems can actually have the effect on the in process time. That means, how much they actually calculate the parameters. Okay. Each path in the path, each point, at each point the cutting parameters are calculated by the adaptive control system, and the actual machining parameters, okay, the optimum machining parameters, they are calculated for each of the points. And since the machining happens at the actual at the optimum cutting parameters, therefore, the time taken is optimum, okay, and it is not like in case of the NC machines. Whereas, NC guides the sequence of tool positions or the path of the tool during the machining. As I said just now, adaptive control determines the proper speed and or feed during the machining as a function of variations in such factors as work material hardness, width or depth of cut. Just see what is written, what is given. Let me explain it to you. Adaptive control system, it determines that what should be the optimum speed or what should be the optimum feed during the machining, and that will be by varying such factors as by variation in such factors as workpiece material hardness, width, depth of cut, etc. in terms of those. Okay. How it is done, we will see this. Now, adaptive control has the capability to respond to and compensate for these variations, okay, these variations in these factors. Now, adaptive control system, they can be used under the following conditions. The in process time consumes a significant portion, because normally the adaptive control, we said that these have the effect on the in process time. So, when the in process time consumes a lot of time, okay, then of course, it makes sense to have some control over that, so that it can be reduced, all right. Then it will be feasible, because otherwise the of course, the process is expensive. Okay. Using the adaptive control system will be always expensive, more expensive than let us say not using that. Okay. Now, there are significant sources of variability in the job for which adaptive control can compensate. Okay. That means, the adaptive control adapts speed and or feed both to those variable conditions, and variable conditions we said that work material hardness. Okay. One example that I was giving, this is an example of the variation in the work material hardness, that there are inclusion of the hard particles. So, the workpiece material hardness is varying, okay, or width or depth of cut, because these are the errors in the process. All right. Now, adaptive control system is a control system that measures certain output process variables and uses these to control speed and or feed. Okay. That means, it will constantly measure the output. Output may be anything, it may be, as I gave you an example, it may be force, cutting force, or it may be the relative movement between the tool and the workpiece, it may be the vibration. All right. It may be many other parameters, it may be temperature, what is the temperature which is occurring. If the temperature is higher, you may actually activate the process to do something, let us say coolant starting, otherwise you are not putting the coolant on. As soon as the temperature goes beyond certain values which will be measured by the temperature sensor, then your feedback control will be working. So, that is also an adaptive control system. So, what I overall mean is that at the output there can be different kind of sensors to measure different outputs. Okay. Either it is a movement of the carriage or movement of the tool post, okay, vibration of the tool with respect to the workpiece and so on. Now, once again, adaptive control system is a control system that measures certain output process variables and uses these to control the speed and the feed. That means, those variables which have to be, let us say in terms of speed, as I said, the speed is varying. So, no sorry, the force, you are measuring the force as an output and you have to stabilize it. So, that can be stabilized by varying the feed or the speed. Okay. These are the two parameters that the adaptive control actually takes as the controlling parameters. Okay. By controlling these parameters, variables can be stabilized. Now, the process variables can be therefore different. So, spindle deflection, okay, force, torque, cutting temperature, as I was telling, vibration, okay, vibration amplitude and power. So, any of these or many others may be, even other examples you can come up with, these can be the process variable. So, if it is if one of them or all of them are important for us to stabilize, then we will be using a suitable sensor which will sense the one of them or all of them, okay, separately. So, all these are separate sensors, and then take those signals to the input, create the error signal and correct the system. Okay. That is the adaptive control system. So, there are two types of adaptive control systems. Okay. One is the adaptive control optimization and another is the adaptive control constraint. Okay. So, adaptive control optimization, as you can see in the slide, this is an index of performance is specified for the system which should be a measure of overall process performance, such as production rate, cost per volume of material removal, etc. Okay. So, here an overall index of performance. All right. Now, we have a production, all right, that overall index of performance is the production rate. So, through the production rate we can actually evaluate that particular production, okay, like that. So, you select, or you as the decision maker, you select the performance index of a particular process or a system, and then that particular performance index objective is that to optimize the index of performance by manipulating speed and or feed in the operation. So, once again, that is the index of performance, it is the index of performance that has to be selected. It can be many, it can be different, that is production rate, cost per volume of material removal, etc., and that has to be optimized, okay, by manipulating the speed and or feed in the operation. So, this is the adaptive control optimization. Okay. Now, second type of adaptive control is the adaptive control constant. Okay. Now, adaptive control constant has a constant limit, and constant limits are imposed on the measured process variables. The objective of the adaptive controller is to manipulate the speed and feed to maintain the measured variables at or lower or below their constant limit. So, this is different than the optimization in the sense that in case of adaptive control optimization, okay, we have the index of performance and that we are minimizing, okay, or we are optimizing, all right. Now, in case of constant, we say that example that I have given, that we have a certain value of the force which cannot be exceeded. Okay. Now, if the tool meets with a portion of the material which is of higher hardness, the force will exceed, and if the force exceeds that value, which is the adaptive control constraint, in this case we are defining, in that case it will be actually changing, or the process itself will manipulate the speed and or feed, okay, to maintain the measured variable at or below the constant limit values. Okay. Meaning that whenever that signal will go to the input and it will be compared with the input signal. So, there will be an error signal produced, and the error signal will automatically change the speed or the feed, so that the force is actually decreased to that value which is required. So, how it is done? That means the tool will be simply retracted or feed is given less, okay, the speed can be decreased, so that the force actually comes down below or to that limit which is given as a constant. So, once again these are the two different types of the feedback control system, adaptive feedback control system. One where we have the you have the optimization, okay, adaptive control optimization. There we have the index, certain index, and that index has to be optimized. In case it is the index is the production rate, for example, then the production rate has to be maximized. So, take the first derivative of that equation and take it equal to 0, it will be the maxima you can get. Okay. But in case of adaptive control constant, you set the value of certain parameter that you are interested in, let us say force, let us say it can be temperature, okay, it can be amplitude of vibration, okay, it can be deflection of the spindle and so on. And then whenever this change happens, then the feed and the speed can be changed by the system itself, adaptive control system itself, so that that parameter which you wanted to stabilize will be activated. Okay. Now, most ACO system, ACO is the adaptive control optimization, they try to maximize the ratio of work material removal rate to tool wear rate. Okay. So, we said that there are in ACO we have to have an index of performance. That index of performance is very popularly used as the ratio of the material removal rate and the TWR, the tool wear rate. So, this has to be maximized, so that tool wear rate can be less and material removal rate can be more. Okay. This is what is these are the two types of the adaptive control systems, and I will give you in my next discussion session some examples that will actually describe how effectively we can use the adaptive control systems and how we can use them actually in practice to what benefit. Thank you very much for your attention.